in town. Now, Miss Copland, we decided as a class that the best way that the students think they're going to learn when I'm away is that when I make the video and then they put their hands up and you can stop the video when they have questions to explain. So, so students, please don't forget, raise your hand, ask questions, right? Asking questions is really good for your learning. Please don't be embarrassed to ask. All right. So today's lesson is first of all, not on quiz, right? Not on quiz. All right. Um, Today we are looking at solving linear quadratic systems graphically. What does that mean? So graphically, you got it. We're going to be graphing. Linear quadratic. This is another one of those terms that you want to add to your list of terminology. Okay, so it's a system, meaning there's more than one equation. A linear one looks like that. A quadratic one looks like that. Do you remember when in grade 10 you were learning about linear systems and you had two lines and they met at one point and we called that the point of intersection? Well, how many points might we have in this case? Well, we may have a situation where we have 2 points of intersection, right? Or instead we'll say 2 solutions. So let's understand what we're going to do today. We're going to understand and explain 3 cases of possible solutions in linear quadratic systems. Okay, when we studied linear systems, one of the solutions was when there was one solution. That's one type. Another one where the 2 lines were parallel. How many solutions were there? You're right, 0. And then there was the situation where 2 lines were coincident, meaning they were literally on top of each other. And in that case, there was an infinite number of solutions because they intersected at an infinite number of points. So let's see what the situations are for a linear quadratic system. So that's the first learning goal for today. The second one is to graph both the line and quadratic function, i.e. parabola, to determine or to find the solutions. So yes, we are graphing lines, and yes, we are graphing parabolas today. Let's move on. Recall, a solution to a linear system of equations is a point that satisfies both equations. By satisfy, we mean if we take a point, x and y, with some numbers, and you plug it into both of the equations, then both of the equations will work. Like left side will equal to right side. That is what a point of intersection is. Okay. That is, the point lies on both functions and is therefore a point of intersection between the two. This year, we are examining 3 possible cases for linear quadratic systems. All right, turn your page. Let's look at these options. Okay, so the first case, I'm just going to zoom in a little bit. The first case is where we have a parabola and we have a linear function or a line cutting right through the parabola and having 2 points of intersection or 2 solutions. Okay, in this case, the line intersects the parabola at 2 points, and this means that there are 2 solutions since 2 points will satisfy both the equations of the line and the equation of the parabola. Meaning, if you take these points, for example, if it's like 6, 5, and maybe this one is like 2, 4, and you plug them into the equation of the parabola and the equation of the line, you will get left side equals right side for each of these points. That's case 1. Case 2 is where we have one solution. And as you can see, this is when the linear function just grazes the parabola. Okay, and so in this case, the line only goes through one point on the parabola. the line would be considered a tangent to the quadratic function since it only goes through one point. So a tangent will always be on the outside of the parabola, and it can really be anywhere. Like I can have a tangent right there, right? And it touches one point of the parabola. Or I can have a tangent here. Or I can have a tangent, I don't know, that one's a bit trickier to draw, okay? But what we're saying is there's only one point of intersection. And that would mean one solution. And then in the third case, we have a case where there are no solutions. And that's also realistic, right? Where we have a parabola or a quadratic function, and then the linear function is, in this case, above it, and they never meet. Or if I have a quadratic function with a positive a value, then my linear function might be somewhere underneath, right? Somewhere where it just will not touch the parabola. Okay? In that case, we have no solutions, and so there are no points that satisfy both equations. Okay? And so we would say there are no solutions in this case. All right, so today we will work on graphing the parabola and the line to see the solutions, but we will also, after March break, we will look at algebraically solving this, right? So almost doing an elimination or substitution situation just with a quadratic and a linear system. All right, let's review the steps for graphing parabolas and graphing lines. Graphing lines takes us back all the way to grade 9. So let's look at the steps. So if we're graphing a line, it is helpful to have the equation in the slope-intercept form. The y-intercept is the b, and the slope is whatever comes before the x. So you start by plotting the y-intercept on the graph. Then you use the slope, meaning the rise and the run, to find the next point. Then you can use the slope again to find more points, right? The more points you have, the more accurate your line is. So here it's saying 3 points are generally enough. Let me do a quick example. X-axis, y-axis. I'll do an equation. Y equals -3 over 2x plus 4. All right, so we start with the y-intercept, and the y-intercept in this case is +4. So we draw a line on the y-axis at +4. Then we're going to take the slope. In this case, slope is -3 over 2. And that's saying the rise is telling us to go down 3. The run tells us to go across 2. So starting with the y-intercept, go down 3. 1, 2, 3 steps, and then 2 across. 1, 2. Draw that line. Now, step 3 is saying more points lead to more accurately drawn lines. So I start at the second point, and I use the slope again to find the next point. I go 3 down, so rise, so you're going 1, 2, 3, and then 2 across, 1, 2, draw another point. And so as you can see, when we have 3 points, we can draw a line that is pretty accurate. Now, when we draw lines, please don't forget to add arrows at the ends of your linear function and try to get your line to go through the entire graph. Okay, if you have questions, ask Ms. Copland, or if you need to, watch a YouTube video. Go online, find how to graph a line, right? I totally understand if you forgot, but you might need to do a bit of extra work. Let's move on to graphing parabolas. All right, so this is when we have an equation in vertex form. Start with the vertex. Okay, let's not forget that the vertex is h comma k. So we're going to draw the vertex. Now, we determine if the parabola is opening up or down. So it's up if a is bigger than 0, and it's down if a is less than 0. Positive, negative. Now, we're going to use the step formula, also known as ordinate differences. Go 1 unit to the right, then 1 up. Go another 1 unit to the right, then 3 up. Another 1 unit to the right, then 5 up. Do you remember that? The step pattern being 1, 3, 5, 7, 9. This is when a equals 1. However, if there is a stretch factor means a does not equal to 1. Then you're going to multiply your steps by the stretch factor. So here's an example. If the stretch factor is 2, right, that tells us that a equals 2, then you multiply each step by 2. So I would write it like this: 1, 3, 5, times 2. So my steps are 2, 6, 10, etc. We're going to do a few examples in the note. So hopefully that will jog your memory how to draw parabolas. Let's go back to this file. Oh no, I hate how that happens. Okay, I need to pause this video. Linear-quadratic systems graphically, you're going to graph the line and the parabola on the same graph, right, on the same axis. Then we'll find the points of intersection. So let's start off with this example. We've got a linear system. Okay, so we'll start with that one. Y equals 2x minus 5. So what do I know about this? Well, I know the slope is 2 and that the y-intercept equals negative 5. However, the slope, I like to have a rise and a run. So I'll write the slope as a fraction, 2 over 1. And then I can say, okay, that means the rise is 2 up and the run is 1 across. So let's graph the y-intercept. Okay, so here, just a quick way of setting the scales on the axis is to write 1, 1. So what you're saying is, okay, these axes go up by 1. Okay. And so in this case, if my y-intercept is negative 5, I'll make it purple. 1, 2, 3, 4, 5. I'll draw my first dot at negative 5. And now I'll use my slope to find the next dot. So if my slope is 2 up, 1 across, 2 up, 1 across, draw a dot. Now I'll do that again 3 more times just to get more dots. 2 up, 1 across, 2 up, 1 across. And so as you can see, I've got a pretty good line, a pretty accurate line being drawn here. It's important to draw accurate lines so that we can find the point of intersections, the points of intersection. Like that, like that. Okay. Arrows at the top and the bottom. And I love labeling functions. Y equals 2x minus 5. Right? If you want to use 2 colors, go for it. Colors I find are really helpful. Now we've got a parabola. Negative 2, x minus 4 squared plus 7. And if we look on the previous page, step 1 said to draw the vertex. of the parabola? Well, the vertex is 4, 7. Okay, so let's draw that. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. All right, that's my vertex. And my step pattern, since A equals -2, that means my step pattern is going to be -2 times 1, 3, 5, blah, blah, blah. And so that gives me -2, -6, -10. I'd get -14, etc. And the negative just tells us to go down. So watch, I go 1 across, 1, 2 down. 1 across, 6 down. 1, 2, 3, 4, 5, 6. 1 across, 10 down. Okay, I can't even go that far. Now, the beauty of parabolas are that they are symmetrical. And so I don't have to count the step pattern anymore. I go 1 across and I match the points so that they're symmetrical. And now I will carefully try to draw a parabola as best as I can. It is really hard on this computer. I find on paper I'm more steady. And don't do what I did. This parabola looks very pointy at the vertex. Try to really show that it's a curve at the vertex. And so I'll label this parabola with this equation. Right, that's great math communication. And so we already see that there are two solutions or points of intersection. And I'm going to label them. So this x, 1, 2, 3, 4, 5, that's 5. So the first solution is at 5. 1, 2, 3, 4, 5. 5, 5. That's the coordinates. Those are the coordinates. And the second solution is at 2, -1. Those are the coordinates. And so I can say, okay, therefore, the two solutions to this system are, and then we state the coordinates, right? So we have 5, 5, and we have 2, -1. Okay, let's try another one. And so hopefully drawing parabolas is coming back to you, right? And drawing lines is coming back to you. In example 2, we are given two equations. However, they're not in the formats that we like. So I'll take equation 1 and rewrite it, isolating y. So I'll bring the x to the other side, and so it becomes -x plus 6. Now, what's the slope in this situation? 1, -1 over 1. Remember, we always want that fraction. Okay, so my slope is -1 over 1, and my y-intercept is +6. Notice that I bring the negative to the numerator. I just always, if there's a negative sign, I will always bring it to the numerator, just in terms of consistency. So the rise is actually telling me to go down 1 and 1 across. All right, once again, let's quickly note that these axes are going up by 1. We label the y-axis, we label the x-axis. Those are important. So we can start by graphing our line. The y-intercept is +6. 1, 2, 3, 4, 5, 6. Okay, and then my slope is telling me to go 1 down, 1 across. I'm going to do that several times just because those points are really close to each other. And now I take that ruler And as accurately as I can, I draw the linear function. And you can use either of the formats of the equation. I'll just call it x plus y equals 6. If you have another way of graphing this equation, like if you like to do that by finding the x and y intercepts, go for it. Okay. Now let's graph the quadratic. So we are given the equation in standard form, which doesn't give us much beyond the y-intercept. So I will complete the square to rewrite this function as in vertex form. Okay, so we're all good at this, right? We've practiced completing the squares. Go ahead and try to be one step ahead of me. So step 1 is draw a bracket around the 2x terms. Step 2, factor out the a value. So my a value is -2. What is left? X squared plus 4. Next, take the b value. Oops, that's an x. Take the b value, divide by 2, and square it. So 4 is a funny one, right? Because it's going to be 4 divided by 2 is 2. 2 squared is 4. So we've got -2 x squared plus 4x plus 4 minus 4 minus 8. Okay, factor that perfect square trinomial into x plus 2 all squared. And remember, as this -4 is exiting the bracket, I multiply it by -2. Okay, so that means -4 times -2 is plus 8. And let's not forget that minus 8. So the 8s cancel, right? They just end up equaling 0. And so I have an equation, -2x plus 2 all squared. That tells me that the vertex is at -2 and 0, right? There's no vertical shift. So it's -2 and 0. Okay, so let's draw that. We've got -2, 0. Here is the vertex of our parabola. Now let's look at the step pattern. So if the a equals -2, then once again, I'm multiplying -2 times my 1, 3, 5, 7, 9, blah, blah, blah. And so I'm going -2, -6, -10. So what do I do with these numbers? Well, I go 1 to the right, -2, 2 down. 1 to the right, 6 down. And I've run out of space. On the other side, 1 to the right, 2 down. 1 to the right, 6 down. Draw a smooth curve. Label your parabola. And what can we say about the solutions? How many times do these two functions intersect? They don't. So we can say, therefore, there are no solutions for this system or to this system. Okay, so those are 2 examples thus far. 3. It is example 3. All right, so we've got example 3 on page 16. So we again have a linear function and a quadratic function. We know it's a linear function because the exponent of this x is a 1, right? So that means, so that would tell us it's a linear function. And then if the highest exponent is a 2, like this x squared, that tells us it's a quadratic function. Okay. And so once again, we start off with the linear function. Now, I've started to use the word function, you may have noticed, and that's just to reinforce the fact that a function is something that has a y and an x, and there's a relationship between them, like there's an equation, and that we can graph a function on a graph. Okay, so let's divide everything by 2 here so that we can isolate y. And so we get x over 2, or 1x over 2. And I do that so that I have a nice fraction as my slope, minus 11 over 2. So what do we know about this equation? Okay, well, slope is 1 over 2. That means rise, 1 up, run, 2 across. So for every step up, we take 2 across. Then we know that the y-intercept is negative 11 over 2. And in this case, because we have to plot it on a graph, it is helpful and it is okay to convert this into a decimal, negative 5.5, so that we know where to graph it. Okay, so let's write our scales. So we're going up by ones again. We have the x-axis and the y, as we should always label. If you would like to put more numbers on the scales, that's fine, on the axes. And my y-intercept is at negative 5.5. 1, 2, 3, 4, 5. Okay. So this is negative 5. This here is negative 6. And so my y-intercept goes right in the middle. And then I use my slope and I go 1 up. So from negative 5.5, 1 up is 4.5, right? So again, I'm between the lines, and then 2 across. Now let's get a few more points. So again, 1 up, we end up in between the 2 points in the middle. Oh, sorry, I don't draw yet. In the middle, and then 2 across. Again, 1 up, 2 across. So having 4 points gives me a better chance to graph more accurately. Okay, arrows and an equation. I'm going to make it easier and use the original equation so that I don't have to write fractions. Okay, that's our linear equation. Now let's look at the quadratic. So for the quadratic, we're given the function in standard form. Y equals 3x squared plus 18x plus 20. And so to start, I will write this in vertex form. And to do that, we complete the square. Okay, so we'll complete the square, isolating the two variables with an x. Then we factor out the coefficient of x, of x squared. So we get x squared plus 6x. Now, watch this, and some of you may be doing this anyway. I'll just continue writing. So I'll take my b value of 6, divide it by 2, and square it. 6 divided by 2 is 3, squared is a 9. So just to save another line, I'll just do it this way. Okay, here I have a perfect square trinomial. This negative 9, as it moves, as it moves out the bracket, I need to multiply it by the a, right? So negative 9 times 3. So I get y equals 3. Okay, so to factor this perfect square trinomial, we have an x, 3 plus all squared, minus 27 plus 20. And finally, let's simplify the constants at the end. Negative 27 plus 20 is minus 7. Okay, so if you struggled with the completing the square with this concept that we just did, then go back to the first lesson, review the homework, review the video, right? By now, hopefully you've practiced completing the square enough times that you feel comfortable doing this on your own. Okay, and so now having the equation in vertex form, we can find the vertex. Ooh la la. So we have -3, -7. And using the a equals 3, we find our step pattern. So how's this? Step pattern times 3. Okay, so our usual step pattern, our basic step pattern is 1, 3, 5, 7, 9. It's all the odd numbers. And so when I multiply them by 3, 1 times 3 is 3. 3 times 3 is 9. 5 times 3 is 15. 7 times 3 is 21, right? We won't go that far. And so as I go one across, I will go, I should start lower. As I go 1 across, I will go 3 up. 1 across, 9 up. Right? That's what the step pattern does. 1 across, 3 up, 1 across, 9 up, 1 across, 15 up. Okay, so we need to start by drawing the vertex of -3, -7. So we are in the third quadrant. Remember, first quadrant, second quadrant, third quadrant, fourth quadrant. So -3 is here. -7 will be one lower. And so our vertex is here. And now, see, I'm wishing I drew my purple line longer. We can extend it. So I'm going 1 across, 3 up, 1 across, 5 up, 1 across. Will I make it? No, I can't do 9 up. Okay, but I can see, because the a value is so high, that means there's a high stretch factor. And that means my parabola will be narrow. Oh my gosh, that was wobbly. Okay, I am hoping you can draw much better on paper and pen. This tablet really makes it difficult for me with parabolas. Okay, and then here I've got this and this. Like that. Like that, right? We try to graph the function as accurately as possible through the entire graph. Now, this was not accurate, right? Because I know it actually goes 9 steps up. So it should actually, the parabola should be going something like that. Okay. Y equals 3x squared plus 18x plus 20. Right? Nicely labeling the equation. And so what is your prediction? What will our line do here? So I need to actually go back and draw a few more points, and I need to go backwards. So if I look at what I did, instead of going 2 to the right, I'm going to go 2 to the left. And instead of going 1 up, I'll go 1 down. So from my last point here, I'm going to go 2 to the right, 1 down, 2 to the right, 1 down. And so as I expand this line, what do you notice? Ooh, isn't that cool? These two functions connect at one point of intersection. Right? This is negative 1, 2, 3, 1, 2, 3. So negative 3. Oh, yeah. Negative 7. It's the vertex. I didn't need, because the linear equation, or the linear function is intersecting the parabola at the vertex, then the vertex is the point of intersection, right? And this is a situation, this is the case 2, where we have a tangent, right? Where this line is tangent to the parabola. And so in this case, we can say, therefore, there is one solution. There is one of negative 3, negative 7, right? There is only one point where where the functions intersect. And I want to show you what we also mean by these solutions, right? We've alluded to the fact that the solutions satisfy the linear functions. So what does that mean? Recall, checks, so checking, checking can be performed to ensure that the solution or solutions to the system satisfy both equations. So this is when we're talking about left side, right side, right? Satisfy means left side equals right side. So we're doing a check. Now in this case, there's more work to do because we have two solutions. So we're asked to check, for example, 1. So here we've got the linear equation and the quadratic. And here are the two solutions we found. So let's start off with the linear equation. And let's start off with 5, 5. So this means that the x is 5 and the y is 5. So we plug that into the linear equation. Right? And the rest is written out as it is. Now we don't move anything to the other side when we're doing a check. Actually, I made a mistake. And it's a good mistake to make because I want to show you that you shouldn't make this mistake. So when we are performing a check, we actually use a table. And one part of the table is the left side and the other one is the right side. So in this case, we have the y on the left side and the 2x minus 5 on the right side. Okay, you don't have to write this equation. You can just immediately substitute points in. Notice I did not draw an equal sign because we don't know that they're equal yet. We're checking if they're equal. So if I see equal signs here, that is a miscommunication. You actually lose communication marks because you're saying, yeah, they're equal for sure. No, we don't know. We're trying to prove that now. All right, so let's sub in that y is 5 and x is 5 as well. So now we simplify each side of the check. The 5 can't be simplified more. 2 times 5 is 10, so 10 minus 5 is also 5. And once we get both sides of the equation equaling, we can say, therefore, left side equals right side. Great. Now we're going to do an identical check for the other point. So once again, we draw our table. And since I know I'm going to be doing more work on the right side, I make my left side column narrower. And I don't need to write the equation again. I can just say, okay, my y in this case is negative 1, right? This is my y, this is my x. So I write negative 1, and then 2 times whatever x is minus 5. In this case, my x is 2. So 2 times 2 is 4, minus 5. Oh, look at that. 4 minus 5 is negative 1. What do I say? Therefore, left side equals right side. So what that means is both of these points lie on this line. This line goes through both of these points. And now we do the exact same thing with each of those points and the quadratic. So I know I will need a little more space on the right side, left side, right side. Maybe the first time I'll just write the equation so we see what I'm doing here. Notice I never brought numbers or constants to the other side of the chart because this is not an equation. Okay, so in the first case, we've got a 5, y is 5, and we've got x is 5. I've got -2, 5 minus 4 squared plus 7. So following BEDMAS, everything inside the bracket is done first. 5 minus 4, well, that's just 1. 1 squared plus 7. Next, so brackets are done, exponents. 1 squared, that's 1. So why don't I go to m, multiply? -2 times 1, -2 plus 7. -2 plus 7 is +5. Hooray! I can say, therefore, left side equals right side. Great. So 5 lies on both functions and satisfies both equations. Let's try the last case, and that's the second solution for the quadratic function. So I've got my left side and my right side. I will plug in the y and x immediately. So y is -1, x is 2. I write -2x minus 4 squared plus 7. So the pink for you is the point we're checking, right? Just so you can follow along graphically what I'm doing. And yeah, once again, we've got some BEDMAS operations. So whatever you can do inside the bracket, 2 minus 4 is -2 all squared plus 7. -2 times, okay, -2 squared is +4 plus 7. -2 times 4 is -8 plus 7. -8 plus 7 is -1. And once again, I can state with confidence that left side equals right side. And lastly, we can make a statement and we can say, therefore, 5 and 2 -1, right, the 2 points, right, let me be a bit more, 2 -1, what do they do? Well, they satisfy both equations. Okay, excellent. Now, if you missed some of these notes, they are posted in the Google Classroom. You have some questions here. There's only 2, which is great, which gives you more time to review for the test. And I also want to show you what else I have for you. Chapter 3, quadratic functions. So if you click on the tab notes, right here we have the notes, some extras, and all the videos. Okay. And once I finish today's videos, I will post today's video for March 7th. Next, SLY absence. Okay, this is what's happening today. So, from the top, we've got the homework video, then we'll have the lesson video, and then at the bottom of today's tab, I have a review for graphing parabolas and lines. If you need more practice, then go ahead and go into this document. Now, it doesn't have solutions, so what you need to do is go to desmos.com, plug in the equation, and it will graph itself, and you can check if you got it correctly. And then I have review for the quiz. Now it's posted here in the March 7 absence, but also under the tab review materials. So review of concepts, review for quiz, right? What do we have? We've got more completing the squares work. We've got warm-up questions that I gave last year, but they're good for the quiz and they have answers. We have a quiz review that I quickly came up with. This is something that you should be able to do. And word problems by Mr. Matheson. These are the solutions from yesterday's homework. Okay, so if you struggled with yesterday's homework with the word problems, then just go into this document and there are really well worked out solutions for you there. Okay, excellent.